today's intro session, I think a good chapter for both physics and science as a whole, I think, is Newton's second law. This law is useful because it actually links two very important concepts when it comes to physics, which is the idea of force and how it relates to motion. Now, before we can delve any deeper, let's first do a little revision on what forces are for us. So a force for us is, we define it as any push or pull, right? That's a very general definition of it. More importantly, we define it as a vector quantity. Are you familiar with vector quantities?
Yes.
All right. Can you give me like a definition of what vectors mean?
No, I've heard of vector and scalar, but I get confused in
All right.
definition.
All right. That's no issue. Well, it's a good idea that we're actually going to be using vectors in this, because force we define as a vector. Why? Because it's a quantity that needs both magnitude, meaning a number,
And direction.
and direction. Exactly. Very good. And this makes sense both on paper and even if you think about it conceptually. So imagine if I tell you that I am currently applying a force of 10 newtons on an object. The first thing you would be inclined to ask would be, okay, where is this force acting, right? Because just saying applying a quote unquote 10 Newton force isn't sufficient information, because say this is the box I have, you might be picturing a force like this. You might be picturing a force like this, from below, from the side, anywhere, right? All of these forces could be 10 newtons, right? So notice how, while their numbers might be the same, their magnitudes or sizes might be the same, they still all have different directions, meaning they all have different effects, right? A force you're applying from the left will act differently than the force you're applying from the top, right? Here we just realize that forces need a direction, not just a number, right?
Yes.
All right, so now that we know this information, that forces need magnitude and direction, we realize that when we talk about combining forces and adding forces, just adding up their numbers isn't enough. Why? Because now you have to cater to the direction as well, right? Because you have such a variety of directions, you will need a slightly different form of mathematics to combine forces, right? So let's see what type of combinations do we do. So for simplicity's sake, we'll be talking about combining forces in one dimension. Combining forces in one dimension. What comes to mind when you think of one dimension?
One dimension. One angle. One side.
One side, yes, that's a very accurate way. Very good. So one side. So one side means that you are acting your forces along one direction, right? Or along one common side or line, right? Think of it like the number line or the x-axis, where you have a central 0 point. All values towards the left, towards the right, are positive. All the four values towards the left are negative, right? All these numbers lie on the same line. Therefore, we call this one dimension. Very good. So in order to understand combinations of forces in one dimension, let's take two cases. So suppose I have the first case where there's this object. I'm applying a force F1. Then you help me by applying a force F2. Now, do you think that with you helping me applying a force on this object, do you think the object will move faster or will it move slower?
At which side? Right or left?
Over here, you're applying it along the same direction as I am, just like in this direction, in this diagram that I made.
Faster.
Faster, right? Very good. So how do you think you would create a combined resultant forces? How would you combine these two?
By adding them?
Exactly. Very good. So here we see that when you have forces that act in the same direction, you will always add up the forces. When you have forces in the same direction, both are acting towards the towards the right, you will add your forces to get the resultant force, right? Now let's
Right.
take another example. So now, sorry, I'm applying the same force F1, but now instead of helping me, you're resisting me by applying a force F2, but in the opposite direction. Now, do you think the object is going to slow down or move faster again?
Slow down.
Slow down, exactly. So here, then if it's slowing down, how do you think the resultant force is going to look like? Now, how will you combine the two?
By subtracting them.
Exactly, very good. So I subtract them by writing this. Now, one question. Why did I write F1 minus F2 but not F2 minus F1? What do you think, sir?
Because it's like from the first side.
Hmm. Think in terms of this x-axis or the number line. Notice how lines acting or this arrow, since it points towards the right, positive values lie there, and when the arrow points to the left, it has negative values. I'm essentially doing the same kind of x-axis concept over here, where forces that act towards the right, I give them a positive value by convention, and forces that act in the opposite direction or towards the left, I by convention give them negative values. So it makes more sense to combine these two forces as F1 with the positive sign minus F2 with the negative sign being given to F2 and the positive sign being given to F1. Here the case is different. Here it seems as if F2 is the one acting towards the right and F1 is acting towards the left, when that's not the case, right? So we want to make sure that our plus and minus signs reflect
Yeah.
the direction. This is something that is important when it comes to forces or combining forces, that your plus and minus signs need to reflect directions. Hence why we can't just simply add up or subtract numbers the way we do in scalar quantities, right? So here we see that when you have opposite directions or your forces are acting in opposite directions, you combine them by subtracting, making sure that the negative sign is always next to that one force which is in the opposite direction. Is this clear?
Yes.
All right, great. Now that we've talked about forces, now you may have noticed that we were subtly discussing motion as well, right? In each case, I was always asking you, is the object moving faster or slower, right? So for instance, in
Yes.
this first case, I was saying you in fact mentioned that the object is going to move faster. In the second case, you said that it's going to move slower. So see, here we have finally made a link between force and motion. So what link do we see? That forces will cause motion to change. This is precisely what we saw, right? And we saw two types of changes in motion currently. We saw the first case we saw when the object moves faster, and the other was when the object was moving slower, right? We saw both these
Yes.
cases. And what caused these two changes in motion to happen? A resultant force. So something that kind of sums up this concept of the resultant force and the effect it causes on motion is done precisely using the second law of motion given by Newton. So what Newton's second law says that, I'll first write down the statement. It states that when a resultant force acts on an object, it makes the object accelerate in the direction of the resultant force. And the quantities we see here that are of mind that we must keep in mind are resultant force, acceleration, and conceptually we want to keep in mind the direction of this acceleration, in that it acts in the direction of the resultant force. So this is precisely what we've been exhibiting over here in these two cases, right? A resultant force creates acceleration. This idea of the object, quote unquote, moving faster or moving slower, that's precisely where we are explicitly talking about acceleration, right? So the formula that links the two is force equals the product of mass and acceleration. M is the mass in kilograms. A is acceleration in meters per second square. And finally, force, F, is the resultant force. Here I'll have to keep note. It's not just one singular force, it is the resultant force. That's hence the subscript R, resultant force in Newton. Now this equation is precisely telling you, or it's reflecting, you can say, both these cases. When your object moves faster and moves slower. Meaning, if I were to draw a kind of relationship between force and acceleration, I see that there is this direct relation between the two. By direct relation, I simply mean that when you increase the resultant force, meaning there is this additive effect, you will see that acceleration increases. Hence, over here, that's why we saw that when your resultant force had this additive effect, you experienced the object moving faster, right? Meaning your acceleration increased. There is this positive aspect to it. Whereas, if your resultant force is decreasing or it's lesser, you would expect your object to accelerate less, or you would expect the numerical value of acceleration to decrease. So here we see that there is this direct relation between acceleration and resultant force. Is this clear?